Hello, my name is Dimitris Amaxilatis, and I'm here to present to you our work together with Alexandros Alexakos and Professor Zaragagis on the forecasting and analysis of energy production from photovoltaic installations. Photovoltaic installations are very important as the generation of power from the sun is a key for the shift of our societies away from fossil fuels. This can be done in two types of installations mainly. Large rural farms that can be installed in locations outside major cities that can provide us with larger energy outputs and also have lower land cost in order to be initially deployed, but then need to transfer their energy from the farms itself to the city centers that are the main energy consumption points of the network. On the other hand, we can have smaller urban installations that are placed inside the cities, for example, on the top of the buildings, that require lower transfer costs for the energy to be moved from the production to the consumption sites, and also help in the self-sufficiency of the cities themselves, but as you can expect, produce much lower amounts of energy due to their sizes. That is quite restricted. Such installations are also heavily dependent on the weather conditions in the nearby areas, as the solar radiation that is received from the panel themselves can be heavily affected when there is rain or cloudy weather. So the nature of photovoltaic energy production is quite unstable and needs to be monitored at all times due to the risk that they can cause for the energy grids and energy grid maintainers, as when the production drops from them, alternative sources need to be brought into the mix in order to cover up the difference. So in order to have these alternative sources ready, we need to have better estimates on the production that is expected in the next day or in the next days from the photovoltaic energy production, as alternative sources can sometimes require a lot of time in order to be brought up to speed and contribute the missing part. So this forecasting can be done either based on historical data, which can be quite inefficient as we do not take into account current weather conditions in the area, but also we can bring into the picture weather forecasts in order to have more accurate predictions and also dependent on sudden changes of the weather in the area of the installation. So in our case, we monitored a solar farm located in Greece with over 22,000 solar panels that are split up into 4 different and independent electrical circuits that can produce up to more than 5 kilowatts of power in a fully sunny day. In order to achieve this amount of energy production, the panels are fixed facing south with a 25-degree inclination in order to guarantee that the maximum power can be generated during every day of the year. So our system is split up into 3 layers. The lowest layer of the system is the on-site sensor infrastructure that collects data from the electrical installation and also from weather sensors recording the irradiance of the sun, the wind conditions, and also the temperature on site. In the middle layer, we have the edge infrastructure that is collecting data from all these on-site sensors and transfer this information to cloud services where we can do forecasting and store the data we record, and as well, and also provide notifications to the owners of the installation and forward the information we collect and generate to grid maintainers in order to take our forecasts into account. So for the on-site data collection, we use the Modbus protocol, and both for the weather devices that we have, and also for the electrical circuit. In more detail, we use the ABB REF 615 feeder protection relay that can provide us with information about the energy production of the park at any given time. And we have a Spark Edge gateway installed for the local data collection and analysis, a device that is compatible with Amazon Greengrass version 2 system that can forward data to the cloud at all times, even when connectivity is not available. Data are kept locally, and then they are forwarded to the cloud using any kind of network that could be available in the site, either a data connection, 4 or 5G or NB-IoT connection, a LoRaWAN, or a satellite internet if it is available. So the Spark Edge gateway acts as a proxy to the local site sensors and continuously polls them, as we said, keeps the data locally so we can have our data safe in case of an outage, and then forwards them to the cloud via the Amazon IoT Core. In fact, in the cloud, we have two parallel lines of data flows. We have on top the weather forecast retrieval that is happening every 24 hours or in smaller intervals if we need to have this. So we can poll a weather service every 24 hours, get a new forecast for the weather conditions, and then generate based on that forecasts about the expected energy production of our power plant. And on the bottom layer, on the bottom path, we have the data coming from the site, from the power plant itself, collected by the Spark Edge gateway and forwarded through Amazon IoT Core to a time series database. Then we can merge the two data flows and use any machine learning technique that we want or any forecasting technique that we want in order to generate either forecasts on or analysis or analytics on the performance of the power station, and forward accordingly notifications to users or maintainers. In these charts, we see how the forecast we receive from the weather service that we use compares to the locally recorded and on-site data. So, for example, we see that the forecast of the irradiance for our given coordinates is quite close to the actually recorded one on site. And the same happens with the outdoor temperature. We see only a very low difference. While on the other hand, we see in the wind speed data that the data we record is quite lower than the forecasted ones, and this is as we understand mainly due to the local characteristics of the area of the installation with some hills nearby causing a drop in the wind levels recorded. So based on the fact that we have a quite good weather forecast that we can use, we now use a physical model in order to forecast the energy production of the site. In fact, we use the PVLib library, a community-supported tool for simulating the performance of photovoltaic systems. And we recreate in this library the setup of our photovoltaic power station, and then feed it with the weather forecast in order to get the expected output of the plant in the next 24 hours for every day in our analysis. And in this chart, we can see how the PVLib library actually overestimates the power production of the site during most of the hours of the day. And this leads us to a prediction that has an average root mean square error of around 710, which is quite high. So in order to see if the problem is generated from our model or from the weather prediction or something else, we also used a machine learning based model in order to forecast the same data. And this is done using the random forest algorithm that is using multiple features in order to generate a prediction for the required amount of energy production. And using this model, we can achieve a much better prediction that is almost identical to the one that we have in our that we record in our system as the actual power production during an average day. And we can see that this model, the machine learning model, has a much lower average root mean square error of around 360. And in this model, the most effective part, the part that has the most effect in the prediction is irradiance, as expected, and the time of day of the forecast. So based on the idea that we now have a much better forecast and a much more accurate forecast for our system, we are able to use this forecast in order to identify times of day in our installation where the power production is abnormally low or even zero. And this was used as a feedback loop in the whole dataset that we have recorded. And this gives us a few days where this abnormal behavior is identified. For example, you can see here in the table that around 11 o'clock on the 6th of August, there was a sudden drop in the energy output of the park that was not expected and could not be attributed to cloudy days, cloudy weather, or any other cause, with the difference from the predicted power outcome being quite high. And in fact, this was a time where there was a electrical surge inside the power plant that caused a part of it to be brought offline, and then the whole park was needed to be brought offline, in fact, for the next few hours due to the same issue expanding in the installation. So we can see that using our model we could identify this problem without prior knowledge of it, and probably in a real world scenario notify the administrator of the park in order to intervene and prevent any damage to the hardware installed in the area. So summing up, we showcase the system that is capable of, on the first place, monitor photovoltaic installations in real time and collect data for their operation in an efficient and always on manner. And on the second part, we showcased how our system can forecast the power generation of the park itself using weather forecast information and the characteristics of the park where we deploy our system. These two methods were these two parts were benchmarked during the period that we refer to, and we evaluate also two different techniques for the forecast of the power generation that showed us how the machine learning method could provide us with a lot better results in our case. As part of our future work, we are still collecting data from the park. We have almost doubled, at least doubled the size of our data set, and we have also added winter months in it with more diverse weather conditions. And we are now in the process of evaluating more methods for machine learning based prediction of the energy output of the installation using techniques like and tools like TensorFlow or SVM. On top of that, we want to further investigate the possibility of analyzing the operation of the park based on the output its energy output, and identify problems inside the installation from this output. So thank you very much, and if you have any questions, I would be happy to answer those.